Hello, students. Today we are going to discuss the topic organohalo compounds. Organohalo compounds. What are organohalo compounds? Organic compounds containing halogen are called organohalo compounds. Contents of the topic: nomenclature. Nomenclature, preparation and properties. Nomenclature of haloorganic compounds, preparation of haloorganic compounds, and properties of haloorganic compounds. Organic halogen compounds or haloorganic compounds. Structure of alkyl halides. Structure of alkyl halides. In this chapter, we are going to discuss about alkyl halides. What are called alkyl halides? Those compounds which contain C bond X bond, where X is a halogen, are called alkyl halides. Alkyl halides are also called haloalkanes. X may be F, Cl, Br or I. That is fluorine, chlorine, bromine or iodine. General formula of alkyl halides is written as capital R dash X, R bond X. R may be alkyl. Alkyl may be methyl, ethyl, propyl, butyl, etc. X may be F, Cl, Br or I. In a molecule of alkyl halide, due to high electronegativity of halogen, halogen atom gets partial negative charge and carbon atom gets partial positive charge. Due to the high electronegativity of halogen atom, carbon gets partial positive charge and halogen atom gets partial negative charge. It means that C-X bond is a polar bond and carbon is electron deficient. So we call it as electrophilic carbon. Carbon is called electrophilic carbon. Electrophilic carbon. Electrophile means electron loving. So nucleophile may easily attack on this electrophilic carbon. Therefore, alkyl halides undergo nucleophilic substitution reactions. Examples are given for methyl halides. Ch3F is methyl fluoride. CH3Cl is methyl chloride. CH3Br is methyl bromide. CH3I is methyl iodide. IUPAC names fluoromethane, chloromethane, bromomethane, iodomethane. The polar C-X bond makes the carbon atom electron deficient in each CH3X molecule. Now, let us discuss the classes of alkyl halides. Classes of alkyl halides. Alkyl halides are classified into three types. They are primary alkyl halides, secondary alkyl halides, and tertiary alkyl halides. Alkyl halides are classified according to the type of carbon atom bearing the halogen into primary alkyl halide, secondary alkyl halide, tertiary alkyl halide. For primary alkyl halides, CH3 bond X and R bond CH2 bond X are given as examples. Both are primary alkyl halides. How can we say CH3X is a primary alkyl halide and R bond CH2 bond X is a primary alkyl halide? Because in these two alkyl halides, the halogen X atom is bonded to a primary carbon. Primary carbon means the carbon which is bonded to only one carbon atom is called a primary carbon atom. So, since halogen atom is bonded to a primary carbon, these two are the examples of primary alkyl halides. Next, secondary alkyl halide. Secondary alkyl halide. RRCH bond X. RRCH bond X. This is a secondary alkyl halide. Why? Because halogen atom is bonded to a secondary carbon. Secondary carbon means the carbon which is bonded to two other carbons is called a secondary carbon. Similarly, tertiary alkyl halides. R3 bond C bond X. In this tertiary alkyl halide, halogen atom is bonded to tertiary carbon. Tertiary carbon means the carbon which is bonded to three other carbon atoms or three other alkyl groups. Each alkyl group may contain one carbon. So, since halogen atom is bonded to tertiary carbon, it is called tertiary alkyl halide. Classes of hydrocarbon group. Classes of hydrocarbon group. There are four types of compounds, halo compounds. There are four types of halo organic compounds or organohalo compounds. They are alkyl halides, allylic halides, vinylic halides, benzylic halides. These four types of compounds belong to organohalo compounds. In alkyl halides, halogen atom is bonded to one sp3 hybridized carbon atom. In all alkyl halides, halogen atom is bonded to one sp3 hybridized carbon atom. You can take an example for this type of alkyl halide, Ch3 bond Cl, that is methyl chloride. In methyl chloride, chlorine atom is bonded to sp3 hybridized carbon atom of CH3 group. Similarly, C2H5Cl. In C2H5Cl, Cl atom is bonded to the CH2 of C2H5. That is also sp3 hybridized carbon. In all alkyl halides, halogen atom is bonded to sp3 hybridized carbon atom. Next, allylic halides. In all allylic halides, halogen atom is bonded to one sp3 hybridized carbon atom, but in third position of allylic group. Similarity is there in alkyl halides and allylic halides. In both alkyl halides and allylic halides, halogen atom is bonded to one sp3 hybridized carbon atom, But the difference is that in allylic halides, the halogen atom is bonded in third position of allylic group. Number 3, vinylic halides. Vinylic halides has a halogen atom to 1sp2 hybridized carbon atom. In all vinylic halides, for example, you take vinyl chloride or vinyl chloride. In vinyl chloride, Cl atom is bonded to sp2 hybridized carbon atom. Benzylic halides. In benzylic halides, halogen atom is bonded to carbon that one atom away from aromatic ring. In all benzylic halides, halogen atom is bonded to carbon that one atom away from aromatic ring. In aryl halides, halogen atom is bonded directly to an aromatic ring. For example, you take chlorobenzene. In chlorobenzene, Cl atom is directly bonded to benzene ring. So in all aromatic halides, halogen atom is bonded directly to an aromatic ring. Vinylic halides. In vinylic halides, halogen atom is bonded to vinylic carbon. Example, vinyl bromide. In vinyl bromide, bromine atom is bonded to vinyl carbon. Vinyl bromide is also called bromoethene. The IUPAC name of vinyl bromide is bromoethene. In allylic halides, halogen atom is bonded to allylic carbon. Example, allyl chloride. IUPAC name of allyl chloride is 3-chloro-1-propene. 3-chloro-1-propene or 3-chloro-prop-1-ene. Examples for other. Next, number 4, benzylic halides. In benzylic halides, halogen atom is bonded to benzylic carbon. So, example, benzyl chloride. In benzyl chloride, Cl atom is bonded to benzyl carbon. Aryl halides. In all aryl halides, X, that is halogen atom, is bonded directly to the benzene ring. Example, chlorobenzene. In chlorobenzene, Cl atom is directly bonded to benzene ring. One more example, para-bromotoluene. In para-bromotoluene, bromine atom is directly bonded to the benzene ring at para position. Nomenclature of alkyl halides. IUPAC names derived from the names of parent organic compound. IUPAC names derived from the names of parent organic compound, alkane or alkene or alkyne or alcohol or aldehydes and so on, with a prefix indicating halogens and their positions. Common names derived from the corresponding alkyl group followed by the name of halogen atom. Common names derived from the corresponding alkyl group followed by the name of halogen atom. Examples: CH3 bond Cl. CH3 bond Cl. Its common name is methyl chloride. Its IUPAC name is chloromethane. It belongs to primary alkyl halide. CH3 bond CH2 bond Br. Its common name is ethyl bromide. Its IUPAC name is bromoethane. It is also belonging to same primary alkyl halide. Third example, isopropyl fluoride. Isopropyl fluoride, its IUPAC name is 2-fluoropropane and it belongs to secondary alkyl halide. Next example, cyclohexyl iodide. Common name is cyclohexyl iodide. IUPAC name is iodocyclohexane. It belongs to secondary alkyl halide. Tertiary butyl bromide. Tertiary butyl bromide. Tertiary butyl bromide. Its IUPAC name is 2-bromo-2-methyl propane. It belongs to tertiary alkyl halide. Methyl cyclopentyl chloride. Methyl cyclopentyl chloride. Its IUPAC name is 1-chloro-1-methyl cyclopentane. 1-chloro-1-methyl cyclopentane. It belongs to tertiary alkyl halide. Two more examples are given. Bromocyclohexene. Bromocyclohexene. 3-chlorocyclopentene. 3-chlorocyclopentene. Now let us discuss physical properties of alkyl halides. Physical properties of alkyl halides. Number 1, solubility. Solubility. All organic halides are insoluble in water. All organic halides are insoluble in water and soluble in common organic solvents. All organic halides may be alkyl halides or halide halides or benzylic halides or vinylic halides and so on. All organic halides are insoluble in water. They are not soluble in water but soluble in common organic solvents. Common organic solvents like ether, acetone, chloroform, etc. Boiling point. The boiling points increases. Boiling points increase with increase in molecular weights. The boiling points increase with increase in molecular weights. It means as the molecular weight of alkyl halide increases, its boiling point also increase. It means the boiling point of methyl chloride will be lower than that of ethyl chloride and the boiling point of ethyl chloride will be lower than that of propyl chloride. So as the molecular weight of alkyl halide increases, boiling point also increases. Therefore, the boiling point increases in the order fluorine less than chlorine less than bromine less than iodine. It means that fluorides have lower boiling point than chlorides, which have lower boiling point than bromides, which have lower boiling point than iodides. Example, the boiling point increases in the order means CH3F less than CH3Cl less than CH3Br less than CH3. Among the methyl halides, methyl iodide will have higher boiling point. As the atomic weight of halogen increases, molecular weight also increases. With the result, boiling point also increases. In an alkyl halide, the halogen is more electronegative than carbon. In any alkyl halide, the halogen is more electronegative than that of carbon. Because of this, the carbon gets partial positive charge and halogen gets partial negative charge. So in an alkyl halide, CX bond becomes a polar bond. Polarity can be found. This polarity increases as the difference between the electronegativity of carbon and halogen increases. Alkyl halides have higher melting points than corresponding alkanes, alkynes because of polarity and molecular weight. Because of these two reasons, as the polarity increases, melting points also increase. As the molecular weight increases, melting points also increase. Let us see the preparation of halo compounds. Preparation of halo compounds. Halo compounds can be prepared by different methods. Number 1, direct halogenation of hydrocarbons. Halogenation means replacement of hydrogen atom by halogen atom is called halogenation. Direct halogenation of hydrocarbons results the formation of halo compounds. Halogenation of alkanes. R bond H is alkane. When an alkane reacts with a halogen in the presence of UV light or heat gives alkyl halide and also HX. It is a substitution reaction. In this reaction, HX is obtained as a byproduct. Here X may be Cl2 or Br2. By this method, we can prepare chlorides and bromides. If you want to prepare chloride, methane must be taken as alkane, chlorine must be taken as halogen. When methane reacts with chlorine in the presence of UV light, gives methyl chloride and hydrogen chloride. So reaction chlorination of methane, it is also called chlorination of methane. Chlorination of methane, the reaction, the amount of product which is obtained in chlorination of methane depends upon the amount of chlorine used. Actually, this is a 4-step process. In the first step, we get methyl chloride. If sufficient amount of chlorine is found, we get dichloromethane, trichloromethane and also tetrachloromethane. Number 2, halogenation of alkenes. Halogenation of alkenes. Let us see the halogenation of alkenes. Any alkene reacts with halogen in the presence of UV light or heat gives haloalkene or alkene halide and hydrogen halide as a byproduct. Here examples are given. Alkene, when reacts with a halogen in the presence of CCl4, if the reaction takes place in the presence of CCl4, we get a different product. 1,2-dihaloalkane, 1,2-dihaloalkane is obtained during the halogenation of alkene in the presence of CCl4. Third example, when an alkene reacts with hydrogen halide in the presence of CCl4, we get haloalkane. Anyhow, haloalkene 1,2-dihaloalkane and haloalkane can be obtained by the halogenation of alkenes. Now, halogenation of alkynes. Halogenation of alkynes leads to the formation of haloalkynes. Look at the reactions. An alkyne reacts with a halogen in the presence of UV light or heat, gives haloalkyne. Same alkyne reacts with halogen in the presence of CCl4. In the presence of CCl4, different product is obtained, that is 1,1,2,2 dihaloalkane. And when an alkyne reacts with hydrogen halide in the presence of CCl4, gives 1,1-dihaloalkane. Anyhow, halogenation of alkynes deals with the resulting different products. When an alkyne reacts with a halogen, depending upon the reagents, different products are obtained. If an alkyne reacts with hydrogen halide, 1,1-dihaloalkane is obtained. Now look at the halogenation of alkyl benzene. When alkyl benzene reacts with a halogen in the presence of UV light or heat, gives substituted alkyl benzene, that is halogenated alkyl benzene. Similarly, when alkyl benzene reacts with a halogen in the presence of iron trihalide, different products are obtained. Presence of iron trihalide gives the para-isomer and ortho-isomer that can be observed in this reaction. When alkyl benzene reacts with halogen in the presence of UV light or heat, gives halogen substituted alkyl benzene. When alkyl benzene reacts with halogen in the presence of FeX3, that is iron trihalide, gives ortho and para isomers. Halogenation of alcohols. Halogenation of alcohols also give alkyl halides. When an alcohol is treated with a halogenating agent, gives alkyl halide. Halogenating agent may be hydrogen halide or thionyl halide or phosphorus trihalide or phosphorus pentahalide, HX or SOX2 or PX3 or PX5. Examples. In the first example, alcohol is taken, hexanol is taken. Hexanol in the presence of PCl3 gives chlorohexane. In this reaction, OH group is substituted by Cl. In next example, cyclohexanol. In the first example, heptanol is taken. Heptanol is taken. When heptanol is treated with PCl3, gives chloroheptane. In the second example, cyclohexanol is taken. When cyclohexanol is treated with SOCl2, that is thionyl chloride, in the presence of zinc chloride, gives chlorocyclohexane. SO2 and HCl are obtained as byproducts. SOCl2 is a good chlorinating agent. In third example, Substituted benzyl alcohol is taken. Methyl substituted benzyl alcohol is taken for halogenation. This substituted benzyl alcohol, when treated with the PBr3, OH group is substituted by Br atom. In last example, tertiary butyl alcohol or tertiary butanol. This tertiary butanol on treating with concentrated HCl gives tertiary butyl chloride. In this reaction, OH group is substituted by Cl atom. Reactions of organic halides. Nucleophilic substitution reactions. Alkyl halides undergo nucleophilic substitution reactions. Why? Because in alkyl halides, carbon atom gets partial positive charge and halogen atom gets partial negative charge. So, polarity occurs in alkyl halide. Due to the electron deficient carbon present in alkyl halide, it readily attracts a nucleophile. So, alkyl halides readily undergo nucleophilic substitution reactions. Nu is nucleophile. Nucleophiles may be hydroxide, alkoxide, amine, cyanide, halide, acetylide, etc. Different examples are given for nucleophilic substitution reactions. Benzyl chloride. Benzyl chloride reacts with sodium cyanide, giving rise to benzyl cyanide. In the first example, bromopentane on treating with a dilute KOH, bromopentane on treating with a dilute KOH, pentanol is obtained. It means in this reaction, alkyl halide is converted to alcohol. Alkyl halides are converted to alcohols. So, by treating with a nucleophile, the alkyl halide is converted to alcohol. Benzyl chloride is converted to benzyl cyanide. In third example, chloropentane on treating with the sodium phenoxide gives substituted compound. And another example, bromopentane is converted to substituted compound. Last example, bromocyclohexane. Bromocyclohexane on treating with the sodium iodide converted to iodocyclohexane. Elimination reactions. Alkyl halides can lose HX molecule to give an alkene. In all elimination reactions, alkyl halides give alkenes. We call these reactions as dehydrohalogenation. Dehydrohalogenation. If the haloalkane is unsymmetrical, example 2-bromobutane or 2-bromopentane, a mixture of isomeric alkene products are obtained. Take the example, this is 2-bromobutane. When 2-bromobutane is treated with concentrated KOH in the presence of ethanol gives 2-butene as a major product, 1-butene as a minor product. In this other example, dibromobutane is taken. Dibromobutane on treating with the alcoholic KOH gives an intermediate compound which on further reacts with sodamide gives an alkyne. In third example, 1,2-dihaloalkane on dehydrohalogenation gives alkyne. In last example, same dehalogenation takes place. Dehydrohalogenation takes place. In all these reactions, dehydrohalogenation takes place, which leads to the formation of different products. The last example, alkyne is substituted alkyne is obtained. Formation of Grignard reagent and its reactions. One of the best uses of alkyl halides is formation of Grignard reagent. Using alkyl halide, Grignard reagents can be prepared. What is Grignard reagent? Alkyl magnesium halide is known as Grignard reagent. R-MgX. X may be Cl, Br or I. When an alkyl halide is treated with magnesium in the presence of dry ether, gives alkyl magnesium halide. By this process, we can prepare different Grignard reagents: methyl magnesium halide, ethyl magnesium chloride, methyl magnesium bromide, etc. From aryl halides also we can prepare Grignard reagents. Aryl halide or halobenzene. When halobenzene is treated with magnesium metal in the presence of dry ether, gives aryl magnesium halide. By this process, we can prepare different aryl magnesium halides. Reactions of Grignard reagent. Using Grignard reagents, we can prepare alkanes. When a Grignard reagent is treated with water, gives an alkane. It means that by the hydrolysis of Grignard reagent, alkane can be obtained. Be obtained by treating Grignard reagent with an alcohol. Alkane can also be obtained when a Grignard reagent is treated with an alkyne. Fourth property is reduction of alkyl halides. Reduction means addition of hydrogen or removal of halogen is called reduction. Here, reduction by zinc metal and acids or reduction by metal hydrides. Example, CH3, CH2, CH2Br. This is propyl bromide. Propyl bromide or bromopropane on reduction by zinc metal in the presence of an acid gives propane. So any alkyl halide upon reduction gives an alkane. Reducing agents may be different. In the second example, bromobutane is taken or butyl bromide. This butyl bromide on reduction with lithium aluminum hydride in the presence of ether and hydrolysis gives butane. So butane can also be prepared by taking butyl bromide. Anyhow, reduction of alkyl halide gives an alkane. Reduction by sodium metal, coupling reaction. And when an alkyl halide is treated with sodium metal gives an alkane. This reaction is similar to that of Wood's reaction. In Wood's reaction, ether may be used as a solvent. Reduction using lithium dialkyl cuprate. When lithium dialkyl cuprate is taken as a reducing agent, it in the presence of lithium dialkyl cuprate, alkyl halide undergoes reduction giving rise to alkane. In this example, lithium diethyl cuprate reacts with methyl bromide giving rise to propane. Thank you.